Hi guys, welcome to week 2 of Marine Science Online. We are going to talk about climate change this week. We're going to sort of go over just some real basics of what causes it, what's happening, and then over the next 2 weeks we'll go into some topics that are a little bit more specific. Before we get started, I'm not going to play the YouTube videos that are sort of embedded into my slides. Those made my lecture really long last week, and also the sound was really bad on some of those videos. So I'm going to go ahead and skip those. Get started. All right, so we start with talking about greenhouse gases when we talk about climate change. Greenhouse gases are gases that trap heat in the atmosphere. So some examples are carbon dioxide, methane, water vapor can even be a greenhouse gas. There's a whole variety of gases in the atmosphere that are greenhouse gases. Some have more of a warming effect than others, but basically, let me show you this diagram here. What's happening is as sunlight and heat energy comes into the planet, a lot of it wants to sort of bounce back out into space. It gets reflected back out into space. Those greenhouse gases trap and absorb that reflected heat trying to leave the planet. They absorb it and sort of trap it in our atmosphere. So basically, if you look here and think of this layer of greenhouse gases in our atmosphere, it's kind of like a blanket that's trapping heat on our planet. Okay. So greenhouse gases are completely normal and natural on our planet. Okay, greenhouse gases are normal, they're natural, we need them here. If we didn't have greenhouse gases on our planet would actually be a lot colder than it is, and most of the things, if not all of the things that live on this planet wouldn't be able to survive. We are the warm planet that we are because of the greenhouse gases that we have. So they're totally natural, they're definitely supposed to be there. The problem is that every year we are adding more and more greenhouse gases to the atmosphere. The way that we're doing that is by burning fossil fuels. And so fossil fuels are coal, oil, and natural gas. These are things that we burn to provide electricity, to run our vehicles, to heat our homes. All of these things, as we burn these fossil fuels, the process of combustion that happens, it releases different gases into the atmosphere. Carbon dioxide is one of those, and methane is another one of those. And those are greenhouse gases. So as we do these things, as we burn these fossil fuels, what we're basically doing is when we drill or we mine for fossil fuels like oil, coal, natural gas, we're taking a source of carbon that has been buried down underground. Fossil fuels. They're the remains of old plants and animals from millions of years ago. And so we're taking that carbon that was once part of their bodies and has been stored underground for many millions of years. We're taking that source of carbon, bringing it to the surface, and burning it. And so you're taking a huge hunk of carbon on this planet from underground, and we're putting it into the atmosphere unnaturally. The Earth would not be doing that on its own. Humans are doing that as we mine and drill for these items and bring them to the surface and combust them, burn them, and that process of combustion releases those carbon compounds like carbon dioxide and methane into the atmosphere. Okay, so this is where the problem starts, is the release of carbon dioxide into the atmosphere. So as that happens, it actually warms the atmosphere, okay? So it increases the temperature of the air surrounding our planet, okay? As the air surrounding our planet is increasing, the oceans are going to absorb some of that heat. And so in turn, you also have the oceans heating, okay? So increased atmospheres also mean increased oceans, increased temperatures of oceans. And we'll go over that in a little bit. So before we get started on this, obviously there is a lot of debate about climate change, and if we were in the classroom, I would probably kind of allow us to have a discussion about it. Whoever wanted to have any kind of an input, we could talk about some questions and concerns, but we're not really in that setting right now. There are definitely portions of climate change that you can't debate. You can't really question it. It's science, it's fact. And then there are other portions that are a little bit more open for debate. And so what I mean by that is you can't debate the fact that we're burning fossil fuels. Okay, we're definitely burning fossil fuels. We know for sure that releases carbon dioxide into the atmosphere. Okay, you can't question that. We could, let's see, if we were at school, we could go out and we could do a lab. I have a carbon dioxide probe. It's attached to a little computer screen, kind of like a phone, and it tells you the amount of carbon dioxide in the atmosphere. You can breathe on it and the concentration will go up because we release carbon dioxide out of our breaths. I've done a lab in the past where we walk outside and we take these carbon dioxide probes around to different vehicles, and you put it next to the exhaust and you turn on the vehicle, and as you turn on the vehicle, the concentration of carbon dioxide goes up immediately, very quickly. And so we know for sure we're releasing carbon dioxide into the atmosphere. It's very simple. It's something that we could model in class and see in class and actually take data on. Okay. The other thing we could do in class is we could take air that's just basic air, and then we could take another container of air that we add carbon dioxide to. And there's a variety of ways we could add carbon dioxide to it that we don't need to go into. But if we then took those two volumes of air, one regular and one with increased amounts of carbon dioxide, and we heated it up with a lamp and then measured the temperature, we would see that the portion of air that contains the more carbon dioxide, it would go up faster. Okay, so this is something we can easily model. And so when we talk about climate change denial, it's not really the facts that most people are denying. I think it's the effects that people are denying, okay? So you can't deny that we're burning fossil fuels. You can't deny that fossil fuels release carbon dioxide, and you can't deny that carbon dioxide has a warming effect on our planet, okay? Those are all definite facts. We've been recording these things for decades. We've got data all around the world coming in on that. Some of the things that are a little bit more debatable, though, I guess, are the effects, you know, as we see increased hurricane seasons and increased fires and droughts and things like that. You know, is it related to climate change? Can we blame everything on climate change? Not everything can necessarily, we can't say that everything is happening because of climate change. And so there are some areas that are up for debate and reasonable debate, but then there are also a lot of people that just say, well, I don't believe in it, it's not really happening. And that's a little bit difficult to do. You basically would be denying facts if you wanted to do that. But there are also arguments like people saying that our planet has gone in and out of these warming and cooling stages, and they definitely have, and we'll look at a little bit of that data. But no matter what kind of argument you want to make, it all comes back to the fact that we're definitely doing these things, and these things are definitely warming the atmosphere. And there's no really denying that. So let's keep going and look at some of the data. All right, so also before we get into that, one other thing I want you to understand, this is something called paleoclimatology. This is a type of science that looks at past climates. So the word paleo, okay, like paleontology means ancient, and then climate has to do with, climate in the atmosphere. So looking at ancient climates on our planet, scientists will go into some of our polar regions, and they'll take what's called an ice core. And it's basically these long, big metal tubes, and they drill them down into the ice. And they have drilled down miles before. And when they bring it up, these cylinders, I guess you would call them, as the cylinders of ice, they're going to contain air bubbles. These air bubbles are packets of air that were trapped hundreds of thousands of years ago at whatever point when that ice was created. And those air bubbles contain information about what the atmosphere was like at that point. And so we can go back in history and we can learn from these ice cores, and we can gather data on what the history of our atmosphere was like. So before we go into that, last week I told you a little bit about what an ice sheet is. Okay, Greenland, Antarctica are covered in ice sheets. And so those are just many, many years of compacted snow and ice that have piled up over and over. So each year you'll have snowfall, and it kind of compacts together. Some of these air bubbles will get trapped. Some years there'll be more air bubbles than others. It just depends on some of the different abiotic factors that are going on, how fast the snow is compacting, things like that. But you'll have a year of ice and snow, and then you'll have another year on top and another year on top. And so it's just a layering and layering and layering. And so the deeper you go into an ice sheet, the further down into history you're going. And so as you pull out these ice cores and you analyze these air bubbles inside of the ice core, you're going back further and further in history the deeper you go. And one thing that we do notice as we go back in history is that climate change is definitely not anything new. As we look at the carbon dioxide levels in these air bubbles and we analyze it layer after layer, we see huge fluctuations. Okay, carbon dioxide has definitely fluctuated over the time over these time periods that we are collecting ice data from. There are a lot of different things that can contribute to that. I have a list here. Okay, so volcanic eruptions, the amount of plant life, vegetation on our planet can play a role in that. And so it's not just the carbon dioxide levels that are fluctuating, but we can also gather information on what the temperature was like at that time as well. There is information from volcanic eruptions in the ice layers. Sometimes we see these layers of just dark ash, and those are periods when we had major volcanic eruptions on our planet, and that dust and ash settled down onto the ice. And so there's a lot of information going back in these ice cores that we can get. So let's keep moving here. All right, so what I'm going to do is go over these sort of indicators. Okay, we have these 10 major climate indicators. We do know that our climate has been changing for millions of years. And so that's one argument that a lot of people make, is that, well, our climate's always been changing, and we've gone in and out of ice ages back and forth, and our climate is supposed to change. Scientists are definitely not denying that. In fact, scientists are the ones that tell you that. Scientists are the ones that research, paleoclimatology, and tell us about the past history of our planet. So we definitely have been in and out of ice ages and definitely had a changing climate for many, many millions of years. So here's the things that are happening today, the things that are recordable, the things that we are taking data on, and that we can actually show and present data on and show change happening over time. So 10 different things. We're going to go by them one by one. Some of these we're going to go into more depth in this week or next week, and so I might go over most of these pretty quickly. Okay, so the first one here is just global temperature rise. As we have been measuring temperature on our planet, we for decades now have been watching it slowly go up and up and up, the average temperature for the entire planet. So the Earth's average surface temperature, and what this means is not the temperature in any one given place, but the temperature of a variety of places all around the planet. When measured and added in together and averaged, that temperature has gone up. And so what I mean by a bunch of different places is, if you look here, this is, these are all of the major labs that are collecting data on our planet. Okay, and so you can see that some of them, based on their color, some have been around collecting data for almost 200 years. Mostly North America and Europe. Okay, and then if you look into the greens and the blue, these are going to be some of the newer things that have only been around for the past 50 years. And so in every we're recording data about the atmosphere daily, monthly, weekly, by the minute in some places. And so scientists from all over the world compile this data, they put it all together, and they come up with an average temperature for the year. And so over the past few decades, we've definitely noticed these average temperatures increasing. Okay, the majority of the warming has increased in the past 35 years. The warmest year that we have had on record was 2016. Okay, 2019 last year was the second warmest. Okay, so it did not beat 2016. But overall, the past 5 years, for the most part, have been the 5 warmest years on record. So every year is not necessarily warmer than the next, but every year that we have had over the past decade is a lot warmer than anything we've had in a few decades. So we are continuously, not every year getting warmer and warmer, but we are continuously seeing warmer years than anything that we've seen in decades. Okay. And this graph here is actually what we call an anomaly. So I'm going to, during your assignment, I'm going to go into how to understand what anomalies mean. So I'm going to skip that for now, so this video is not too long. Okay, so what this doesn't mean, global warming, and you'll notice that a lot of people don't say global warming anymore. We say climate change instead. And global warming is not really the best term to use, because although the entire globe on average each year is warming and warming and warming, and we're seeing warming trends, not every single place is warming. Places are still going to have blizzards. Places are still going to have record cold events. But on average, when you average everything together, there's definitely a warming trend happening. Okay. In fact, some places, because of climate change and different changes in the atmosphere and different changes in ocean temperatures, some places are even experiencing colder winters than they're used to. Okay. So climate change does not mean that every single place is warmer and warmer. It doesn't mean that places aren't still going to have massive snowfall events. It just means that overall, let me move this for a minute here. Overall, there is a definite warming trend on our planet that you can see and observe and measure and take data on. Okay, a temperature anomaly. So again, I'm gonna explain this to you in another video during the assignment. But a temperature anomaly is a change from a reference or a background value. And so what we'll do a lot of times in climate science is we'll take an average, like a 50-year average or a 30-year average on a temperature for a particular location for a particular month or a particular day of the year. We'll take an average of that month or that day of the year over a variety of years, and then we compare that long-term average to this year's average or a particular 1 day or 1 month average. And so what you're doing is comparing and seeing this year, is it higher or lower? Is it warmer or colder than a long-term historical average? Okay, and that's called an anomaly. And so I'll explain that a little bit better during your assignment. Okay, this is an example of an anomaly, a map showing temperature anomalies. And so for the month of April 2016, any place where you see red, that means that it was 2, 3, 4, 5 degrees warmer on average. April 2016, where it's red in those places, was 2 to 5 degrees warmer than April's from 1951 to 1980 average. So for these 30 Aprils averaged together, 2016 was warmer in all the places where you see red, slightly warmer in all the places where you see yellow and orange, and any place where you see blue or white, either no change or actually cooler. Okay, so that's 1 month compared to 30 years of that same month all averaged together. And so the temperature shows how it changes from that 30-year average. Okay, so the second thing that we are measuring and observing on this planet is shrinking ice sheets. So Greenland and Antarctica are our two major ice sheets on this planet. They are miles thick, Greenland being in the center and its thickest place about just over a mile thick, whereas Antarctica is almost 3 miles thick in the center. Okay, again, this is many hundreds of thousands of years of snowfall just compacted. Okay. So if you look here on this map, you'll see we have the two major ice sheets. Measuring melt from ice sheets and thickness, it's very complicated science. They actually are, there's new technology where they actually use lasers on satellites to measure the thickness and the melting. So it's a pretty complicated science, but overall we're measuring the ice sheets are getting smaller. And Antarctica, there are actually some portions of Antarctica, the ice sheet is actually getting larger. But in other places it's getting smaller, and overall Greenland is definitely losing the ice sheet. In general, we tend to see more of the climate change warming effects happening in the Arctic than in the Antarctic, and that's for a variety of reasons I'm not going to have time to go into right now. But ice sheet in Greenland definitely smaller, getting smaller over the years, melting. And Antarctica, some places it's getting smaller, while in some places it is actually it is not getting smaller in all the places in Antarctica. And so this is what spring and summer looks like on an ice sheet. You get these lakes and rivers and just this meltwater from the top of the ice sheet that kind of cuts out of the ice, and it makes these really pretty different views. Nothing like you've ever seen before, so really cool. And then that all makes its way out to the ocean. Okay, the next thing is rising sea levels. So as you have this happening, let's go back here. As you have this happening, you have water that is many years of compacted snow making its way from land, from the top of these ice sheets into the ocean. If that happens enough, it's going to raise the level of the oceans, and that's called sea level rise. The other thing that happens is there's something called thermal expansion, and a lot of different materials in general, as they heat up and as they warm up, the atoms start moving around quicker, and there's a lot of chemistry to it, but basically things will expand as they warm. And so that actually happens to the ocean. And so in the oceans, we have this combination of what we call thermal expansion happening, okay? And then we also have the melting of ice on land, the glaciers and the ice sheets that's making its way to the ocean. And these two things are having a very small impact on sea level change, but it is in recent years enough that we have actually been able to measure it. There are a lot of places that are experiencing problems. I'll post a video from the Florida Keys, for example. There's some flooding that goes on that people are seeing more and more. If you look at what has happened in some European countries, I'll post some videos on those so you can see. But over the past couple of years, there have really been some stories coming up where you can actually see the effects of this sea level rise happening. One place that is really susceptible to these issues is going to be the Maldives in the Indian Ocean. This is the lowest lying nation in the world. And we've talked about these islands before when we talked about coral atolls. Because they're so low lying, they're very exposed to the ocean, and so only a couple of inches of sea level change will make a big difference for them. These are the predictions for sea level rise. Let me move myself here. So the International Panel on Climate Change is this big report that comes out every year, and this is a lot of data all compiled from scientists around the world. And so their predictions for sea level rise range anywhere up to about 2 feet. Okay, and so this is between now and 2100. So this is 80 years, over the next 80 years. Okay, how much they believe that sea level will rise. And so you can see that some of these other scientists, other researchers have done models, and they've come up with higher numbers. Okay, so maybe 4 or 5 feet, 2, 3 feet. But the International Panel on Climate Change, which is what is kind of the most trusted report out there, it's just the biggest portion of scientists working together, says up to about 2 feet, which doesn't sound like a lot, but when in coastal areas, that it is a lot. It makes a big difference. You're talking about storm surges being higher by 2 feet. Your strongest tides of the year being higher by 2 feet. That is a big change. And this is actually a little bit outdated. This was a 2007 IPCC report. Last year, one came out, and they've actually upped their predictions by a little bit over closer to 3 feet. Right, so this is a little bit outdated. So a couple of feet is what is basically, for the most part, expected. Now, sometimes you see things on the internet about, major cities being flooded or all of Florida being flooded. So one thing I wanted to make you realize is that, here's one, for example, you could find online, 60-meter sea level rise. Well, that's over 100 feet. Okay, we're talking about 2, 3, maybe 4 feet at the most, being what most of these scientists have predicted. And then you've got this here that's over 100 feet. So make sure when you see things online that you don't believe everything that you see. This is extremely dramatic and not anything that's ever going to happen in your lifetime. It would take like all of the ice on the planet melting in order for this to happen, and that's not going to happen anytime soon. All right, increasing carbon dioxide. There's a place in Hawaii called Mauna Loa. It is a volcano way up high into the atmosphere, and there is an observatory lab there. They've been collecting data for many, many years. So you're going to look at that graph during your assignment this week. But we can see a steady increase, and I'll show you that in a minute. There's a steady increase over time in carbon dioxide. Okay, this is showing carbon dioxide levels throughout history based on ice core data. And you can see carbon dioxide has fluctuated up and down. However, the highest rate of carbon dioxide previous to modern times was a concentration of about 300 parts per million, okay? Based on what we know from ice cores and those air bubbles, the air trapped in ice, okay? As of now, 2020, we're at about just around 410 parts per million, okay? So right now, we have a concentration of 100 parts per million more than anything we ever detected in any of the ice core samples that we have found. So assuming that science is good science and that data collection is good, and we are actually making good assumptions based on that ice core data, we are seeing a level of carbon dioxide in our atmosphere now that is higher than almost the past million years, higher than anything that we see in the ice core data from 800,000 or very close to 1 million years ago. Okay, here is that increase here. We'll look at this again in the assignment. I'm going to keep going so we don't make this video too long. Declining Arctic sea ice. We're actually going to talk about this a lot more in detail next week, so I'm going to skip over it real quick for now. But basically, as the sea ice in the Arctic Ocean melts in the summer and then refreezes in the winter, if you look summer by summer, you slowly start to see less and less ice, more and more ice melting, more and more ice melting each summer. So this is what you see in the winter, okay? And this is what you see in the summer. And so you expect this difference between winter and summer. It's that this chunk that's left in the summer tends to be getting smaller and smaller, okay? And this is something that we can record. This is another one of those things that you can't debate. We have satellite images, Okay, ever since we've started sending things up into space, taking pictures of our planet, we've got photos, we've got pictures of the Arctic Ocean, and you can see what's covered in ice and what's not covered in ice. And summer by summer, if you look at, the past 50 years or however long we have those satellite images, you can clearly see that we have less ice in the summer now than we used to. And it varies year by year. On average, here's the average amount of sea ice extent from 1981 to 2000, so another 30-year period, okay? And then September 2016, much, much smaller, almost half the size of that 30-year average. Okay, and so you can just see the decline here. In addition to that, the ice is also thinning. It's not just disappearing, but when it does come back, it's thinner. We'll come back to that later. Okay, warming oceans, like I said, as the atmosphere warms, a lot of that heat energy is going to be absorbed by the oceans. And so you've also got increasing ocean temperatures happening. Okay, we'll talk more about this, some of the specific species that affects. Glaciers. Glaciers, oh, I forgot my picture here. Gone. Glaciers are rivers of ice, you learned last time. Glaciers are something that are kind of like ice sheets. Ice sheets are actually very, very large glaciers. So glaciers are, again, a piling up year after year of snowpack. And so most of the glaciers that we have on our planet have been around for thousands of years. So glaciers are not something that come and go year by year. And so if you look at this picture here, almost as long back as we have photographs people took of glaciers. And you can compare them to today. And compare them to all these times in between. And so what you're seeing here, this change, has been recorded in glaciers all over the place. Glacier National Park, Montana, 150 glaciers when it was declared a national park in 1850. Today there are only 25 of those left. Okay, so we are losing glaciers like crazy all over the world. And so again, lots and lots of photographs if you just look at the comparisons here. And this is not like sea ice. This is not like snowpack that you expect to melt back every year and then come back in the summer. That's not how glaciers work. The top layer might kind of melt a little bit in the summers and then you have new snowpack compiling. But glaciers have been around for a very long time. They are not an annual, seasonal type thing. And so when a glacier, when a big hunk of it disappears, it's not coming back the next year because that was thousands of years of snow packed together. And so you can see the retreating of this glacier over time. Okay, and so again, there are pictures all over the world that you can do these comparisons before and after. And again, once they're gone, they don't come back. This is kind of a cool graph. It's showing around the world, any place where you see blue is where a glacier is actually getting thicker or getting bigger. And any place where you see red or orange or yellow are going to be places where glaciers are getting smaller, so melting away. And so while we definitely have some glaciers that are getting bigger, you can see the overall effect on the planet right now is definitely that we're losing glaciers. Okay, and I think this is the last one, or we're getting close to the end here. Extreme weather events. So more blizzards, more tornadoes, more severe thunderstorms, more hurricanes, more heat waves, more droughts, more wildfires. All of these things are all over the news year after year. It seems like we have a lot of them. This is one of those things that really is debatable, I think. Most likely warming oceans are leading to more hurricanes. More heat waves are leading to more wildfires, more droughts. A lot of it can definitely be related to a changing climate. But then again, you can't, every time we have a bad hurricane, say, oh, we had this hurricane because there's climate change. Climate change caused this hurricane. That's not really the case. But if you do look here, and so again, that's one of those areas that's maybe is a little bit debatable. So while there are some things that you can argue and debate and go back and forth on and maybe attribute to climate change or say, no, it's not related to climate change, so some things you can debate, and that's okay. I would say that this would be one of those things that's a little bit more open for debate, that you can't really say, you're not 100% for sure what's happening. And all of these events, as well as we measure and count wildfires and droughts and severe weather events, if you compare us to 1980, I think we collect data better. We know in every corner of the world what's going on a lot better than we did many years ago. So the data collection might be a little bit better. And so anyways, if you're looking at this graph while I'm kind of talking on and on, you can see that a lot of these events, we've seen an increase. And back in the 80s, did we really have only 300 severe weather events, whereas today, we're closing in on 1,000? Did we just take better data than we did back then? You'd have to really read about this research and what was done here to collect this data to know. But this is definitely a drastic increase in the number of severe events. This is just showing right here, so moving in this way, these things have more and more strong evidence to support that climate change is affecting them. So heat waves, coastal flooding are definitely more impacted for sure by climate change. Whereas you go further this way, things like tornadoes and hurricanes, there's not so much evidence that can 100% tie it into what is happening in our climate and our atmosphere. So a little bit more questionable. Okay. Ocean acidification. As there is more carbon dioxide in the atmosphere, that carbon dioxide will get absorbed into the ocean. Okay, that carbon dioxide will react with water to create something called carbonic acid. The more carbonic acid you have in the ocean, the lower the pH will go. It's an acid, so it brings down the pH. Okay, there are a variety of ways that ocean animals are affected by this, and so I am going to save this for a little bit later because we're going to go into this in a couple of weeks in a little bit more detail. This is permafrost, so this is frozen ground, so you've probably heard of permafrost before. Okay, we have a thawing permafrost. A good chunk of our land in Russia, Alaska, Canada, all of those places kind of circling around the Arctic Ocean, a big hunk of them is made up of permafrost, and the warming atmospheric temperatures are thawing that permafrost. As that permafrost thaws, it is releasing in a variety of different ways, but basically as permafrost thaws in a couple of different ways, methane is released from the ground into the atmosphere. Methane is a greenhouse gas, just like carbon dioxide. It's actually a stronger greenhouse gas than carbon dioxide. And so this is something that we call a feedback loop. Whoops. As you are adding more methane to the atmosphere, it's creating a warming effect. The warming effect is then going to melt more permafrost, which is then going to release more methane, which is going to warm the air. And it's this whole cycle. And it's actually feeding into itself. So it's what we call a positive feedback loop. So it's just one more thing that's happening that we're measuring. Anything, so if you can look at this here, it's hard, it's a little bit difficult to see what you're looking at. Okay, so here's Alaska, all right. All of these pieces of land that are purple are where we have permafrost on this planet. A little bit of it in the South Pole along Antarctica, but most of it's around the Arctic. All right, and so I got that a little bit shorter. I almost reached 40 minutes again, sorry. But that's it for climate change. So go ahead and read the instructions on the assignment, watch the extra videos that we didn't play, and take the quiz, and that will be it for this week. And we'll talk a little bit more about climate change next week, some specific details. All right, bye guys. Sorry it was so long.